6.4 work. Okay, so first of all, we talk a little bit about force. Force is mass times acceleration, or mass times the second derivative after the respect to t. So sometimes it's useful to look at it this way. Work is force times distance. So if you've taken like a basic physics class, then it's like if you're pushing a rock along the ground or pushing a block along a surface, then the work is going to be the force that you're exerting on the block times the distance that it moves. Now, if the force is variable, so sometimes the forces can vary, then you're going to use an integral. Okay, so this is basically what the variable force. And this last one is with springs. This only applies to springs. Okay, so the force that a spring exerts is equal to the spring's constant times the distance from the equilibrium position. Okay, so this x here is the distance, or actually it's not distance, but rather displacement from the equilibrium position. And the force will be in the direction back towards the equilibrium position. Okay, so yeah, okay, so now let's go ahead and get into the homework, and we'll bring up these topics, and hopefully you'll be more familiar with all these things when we're done with the homework. Okay, so number one, how much work is done when a hoist lifts a 260 kilogram rock to a height of 9 meters? Okay, so again, the force is mass times acceleration. In this case, the mass is 260. Acceleration is the gravity, okay, which we take to be 9.8 meters per second squared. Okay, now this is in kilograms, it's in meters, so we don't have to worry about it. And the work is going to be the force times the distance. So it'll be this 260 times 9.8 times the distance of 9. Okay, and so that would be just a second. Let me calculate this really quickly. $22,932. Okay, now I did that by just using this formula here. I did it using that formula there. Now, if you want to, you can use this formula here, if you want, and just say you're going from 0 to 9 of the force, which would be 260 times like that. But you're going to end up with the same thing here. You'll just end up the same thing. Okay, so let's go on to the next problem, number 2. Shown is the graph. Here's the graph of a force function in newtons that increases to its maximum value, then remains constant. So the force was building up steadily until after 16 meters, it becomes constant 60 Newton force on an object. And the question is, how much work W is done by the force in moving an object a distance of 32 meters? So from how much force does it take to move from here to here? Okay, so remember that the force is equal to, the work. Sorry about that. Work is equal to the integral. So it's going to be integral from 0 to 32 of the force. Okay, so that's the basic formula right there. Now, but what is the force? Well, we know that after, if x is greater than or equal to 16, and then the force is going to be 60 because it's up here, 60. That's that part there. But right here, this is a line, and it goes through that point and that point. It goes through the origin, so we're looking at line right here for this first part. It goes through the origin, so that's 0, and the slope would be what, 60 over 16. Which is 15 over 4. Okay, so 15/4 is the slope. Okay, so that's 15/4 x when x is between 0 and 16. Okay, so I'll just write that here just to be clear. Okay, so you're integrating this function right here from 0 to 32. So from 0 to 16, the function is 15/4 x. And from 16 to 32, it's just 60, like that. Okay, so this is going to be 15/8 dx from 0 to 16. And this is going to be 60x from 16 to 32. And let's see. This turns out to be 480. This is 960 for a total of 1,440 joules.
I have a question.
Okay, so yeah, go ahead.
So like, because like just taking the integral is just taking the area under the like curve and line, can't you just split it into like take the area of like the 0 to 16 is like a triangle? So like the 1/2 base times height plus the rectangular length times width.
Exactly. So this area here is what is it? 16 times 60?
Yeah.
This area is 1/2 16 times 60. Okay, so it's going to be 1/2 16 times 60 plus 60 times 16. Yeah, exactly. It's just going to be the area under the curve because it's that. Yes, so that's a perfect way to do it as well. Maybe it's shorter if you realize that. Yeah. Okay, number 3. Suppose that 5 joules of work is needed to stretch a spring from its natural length of 36 centimeters to a length of 51 centimeters. Okay, so here is what we said about springs. The force of the spring is the spring constant times the displacement. Okay, so 36 centimeters is the natural length. Natural length means that this is when x is 0. So 36 corresponds to x equals 0, which means that this corresponds to 51 minus 36, which is 15. Okay, so this corresponds to 15. Now, what they're saying is that this is a little bit confusing because what this is saying is that 5 joules of work is needed to stretch a spring from from its natural length to a length of 15, okay? So let's come over here and try to make sense of what this is. And this one you really have to, some of the problems in this section, you really have to read them carefully, because sometimes when it introduces a problem like this, the most basic way would be, the most logical thing would be, well, how much force is required to stretch at a certain distance? That would be the most easy thing to measure. Okay, but instead they give us this really complicated thing, which is actually the work. So the work, 5 joules is the work, but it's also equal to the integral, because you're going from 0 to 15. Another thing that's really, the other thing that can throw you off here is that here we're talking about centimeters. So because of that, then it's the best thing to do, because joules is associated with meters, okay, and newtons, okay. So you can't, if you're talking about joules here, then it's probably best to change centimeters to meters. Okay, so that's 0.15 meters. Okay, so that means in going from 0 to 0.15, then this is going to be your, then this is, and then your force is kx, because we know from the force is kx. Okay, and so you're going from 0 to 0.5, and that's going to be 5 joules. Okay, that's basically what that's telling you. Okay, so it's probably best to calculate this and figure out what k is. So if you integrate this, you get k x squared over 2, and that goes from 0 to 0.15. And so this is going to be k times 0.15 squared over 2, and that's equal to 5. And I did it on the calculator, and I solved for k by dividing by 0.15 squared and multiplying by 2. So I got 444 with a bunch of 4s repeating. Okay, so that's what I got there. So now it's asking how much work is needed to stretch it from 41 to 46. Okay, now since 36 is the equilibrium position, then 41 corresponds, hold on. Okay, so 41 corresponds to 0.05 meters, and 46 corresponds to 0.1 meters. Okay. Okay. So the work is going to be integral from 0.05 to 0.1 of this 444.4 repeatings times x dx. Okay, so I guess if you divide all this by 2, then you get 222 when repeating that 0.2 repeating from 0.05 to 0.1. Hold on, excuse me. That should be x squared. So the integral of x is x squared over 2, so I'm dividing this by 2. So that's going to be 0.1 squared minus 0.05 squared. And that works out to about approximately 1.67. It says rounded to 2 decimal places. I got 1.666 repeating 6s. I round that off to 1.67, Okay, and then finally, part B. How far beyond its natural length will a force of 25 newtons keep the spring stretched? Okay, so here, this one goes back to here. We know that this is 444.44, repeating x. So replace this with a 25 right here. And x would be 25 over 444.4, which is about 0.056. Well, 25. But that's in meters, and the answer that they want is centimeters. So just move the decimal place over 2 places. And they also say to round it off to the nearest decimal place. Okay. Okay. So just a second. Okay. Any questions about that? Okay, let's move along to number 4. It's another spring problem. Wow. Okay, so a spring has a natural length of 26 centimeters. Compare the work W1 done in stretching the spring from 26 to 36 with work W2 done in stretching it from 36 to 46. Okay, so the natural length is 26. That means x is 0 there. 26 would be, that's 0. And 36 would be 10 centimeters, which corresponds to 0.1 meters. And then 36 corresponds to, again, that's 36.1 meters, and then 46 would correspond to 0.2 meters. Okay. Okay, so W1 will be the integral from 0 to 0.1 of k x dx. W2, in the meantime, will be the integral from 0.1 to 0.2 of kx dx. It doesn't tell us what the spring constant is, and it doesn't look like you're going to be able to, from this information, you're not going to be able to figure out what it is. But it doesn't matter. Okay, so integrate this. This is k x squared over 2 from 0 to 0.1. And when you plug a 0.1 in there for x, you get 0.1 squared over 2, which is 0.01 k over 2. And this one is, you're evaluating from 0.1 to 0.2. So that's going to give you k times 0.2 squared over 2 minus k times 0.1 squared over 2. And this is going to be 0.04 k over 2 minus 0.01 k over 2, which turns out to be 0.03 k over 2. Okay, or this one would be 0.0005 k, and this one would be 0.015 k. Okay, so this is W1, that's W2. Okay, so this is the answer for W1. It's in joules, and this is the answer for W2. And then you notice that this is 3 times that. So W2 is equal to 3 times W1. Okay, any questions on that? Okay, great. Let's move on to number 5. A heavy rope. Oh dear. Okay, so here's you have a rope. It's 60 feet long and weighs 0.7 pounds per foot and hangs over the edge of a building 150 feet high. Okay, the 150 feet here is actually not relevant, except in the fact that this 150 feet is more than the 60 feet. So the rope is completely dangling off the side of the building, completely. It's not like touching anything down below. Okay, so the full weight of the rope is off the building. Okay, so part A, how much work W is done in pulling the rope to the top of the building? Okay, show how to approximate the required work by a Riemann sum. Okay, so this one, remember that force is equal to K times, no, is equal to, I'm sorry. Work is force times distance. Okay, so going back to this formula here, not necessarily the integral, but you can think about it as an integral. You can also think about it in the integral form, but I think it's easier to look at it like this right here, even though this is an integral. But the way that you look at it right here is you think of the rope. So if we have the building right here, and then we have the rope dangling down the side, and you're going to pull that rope up. If you look at like a particular part of the rope right here, a little piece right here, and then how much work to take that little piece of rope all the way to the top? That would be the weight of that piece times the distance that it goes. Okay, so this piece up here at the top, it's already at the top, so it doesn't have to go very far. And this piece here doesn't have to go very far. Okay, so if you think of this being 0 and this being 60 right here, think of, and then maybe 30 in the middle. So you have a scale like this. If you put that as your scale, then the pieces of rope that are down here, it requires more work to get them to the top than the pieces that are already close to the top. Okay, so the work is going to be that's required if you integrate from 0 to 60 here, and it's 0.7 pounds per foot. And pounds is the force. Okay, so pounds is a force, and it's 0.7 pounds per foot. And this is 60 feet right here. So it's 0.7 x is and this is how far it goes. Okay, so if I want to label this part, this is the force, and this right here is the distance. This x is the distance. So this is x right here. This is the x right here. Okay, that would be the distance. Okay, and then right here it's 0.7 times x sub I for your Riemann sum over the appropriate integral, and the delta x kind of fixes everything there. Okay, great. So now we just have to integrate. We just have to evaluate this integral, and that's integrating 0.7 x gives you 0.7 x squared all over 2 from 0 to 60. So that's 0.7 times 60 squared over 2. Which turns out to be 1,260 foot-pounds. Okay, so 1260. Okay, great. Part B. How much work is done in pulling half the rope to the top of the building? Okay, so here they just want to pull half of the rope up. So what you can do for this part, I guess the best way to look at this part right here, in my opinion, is instead of having a rope that's 60 feet long, okay, so you want to pull, you still have the full entire rope hanging off the side of the building. You just want to pull it up halfway, right? You just want to pull, so this point, so this halfway point of the rope gets to the top. But all this is just going to shift up 30 feet. Okay, so rather than think of it like this one, you can think of it as a rope that's 30 feet long with a weight attached on the end. Okay, and this weight on the end would be the weight of the other 30 feet of rope. Okay, that would be equivalent to just doing this one. So having a weight like that would be equivalent to having the full rope. Okay, now this weight right here, which we'll look at it with the blue, that one is because the rope is, because this part of the rope is 30 feet long and it's 0.7 pounds per foot, then that weight of the rope is going to be 21 pounds. Okay, so that part's going to be 21, so 21. Okay, so we get 0.7x plus 21, and you go from integrate from 0 to 30. That will give us the answer. This part right here, let me write that better. 0.7 x sub I. Okay, you're supposed to write x sub I here. Plus 20. Okay, that would give it to you. Okay, so we have, if you integrate this, you get 0.7 x squared over 2 plus 21x, and you're evaluating that from 0 to 30. .7 times 30 squared over 2 plus 21 times 30. And that, if you calculate that, you're going to get 945. And I'm pretty sure that's about 3/4 of the total work. That's about 3/4 of the work required to bring the rope all the way up. Just because once you pull up half the rope, then it becomes easier to pull the rest up. Okay, any questions on any of that? Okay, let's move on to number 6, which is the last problem for the day. Okay, here we have an aquarium, 7 meters long, 1 meter wide, and 1 meter deep. It's full of water. Okay, find the work needed to pump half of the water out of the aquarium. So you're going to pump half of the water out. Use 9.8 meters per second squared for gravity, and the fact that the density of water is 1,000 kilograms per cubic meter. Okay. So let me try to draw a picture of the situation. So it is 7 meters long, and so that's 7 right there. It's only 1 meter wide, so 1 meter there, and 1 meter deep. So this is 1 meter here, okay? So this 1 meter deep is this one. And then the 1 meter wide is this one here. And then the 7 meters long is that one. Okay, now again, we're gonna focus on this. Force is equal to, or I'm sorry, weight is equal, no, work is equal to force times the distance. And essentially the density of the water. So if you think about a sheet of water, like right here. Just think about just a sheet of water. Think about that water, and you're going to think about lifting that water up to the top of the aquarium. Just that water lifted up to the top of the aquarium. Okay, just think about that sheet of water lifted to the top. And it says you're pumping out half of the water, so that means that if that's the halfway mark, then if we set our scale here and make that 1/2, so that's x equals 0, this is x equals 1/2. Okay, and so you're going to integrate from 0 to 1/2. To kind of set it up right here, maybe this is not the way that I would have done it if they didn't force me to do an integral that goes from 0 to 1/2. I might have done it a different way, but since that's what they're doing, then I look at it that way. Okay, and so with the values of x in here, this has to be lifted from there to there. If we make that top point 0, this is a typical x, and that sheet of water has to be lifted to the top. Now, how much does that sheet of water weigh? Well, if we look at 7 times 1 times 1, no, 7 times 1, I'm sorry, too many ones there. 7 times 1 times 9.8. So let me look at the units. So 7 meters times 1 meter times 9.8 meters per second squared times the density of water, which is 1,000 kilograms per meter cubed. And here's where the meters get all canceled, and you have kilograms per second squared, which is the unit of force here. And that is 68,600. Okay, so this will be 68,600x. So again, this part right here is your force part, and this part right here is your distance. Actually, the dx is also part of the force, because the dx is, measuring the thickness of the water sheet. Okay, so the 68,600 dx, that's your force part, and then your d, because that's the weight of that sheet of water, and then the d is the distance that you're lifting up to take it to the top. Okay, and so then that means that this is going to be 68,600 x sub I in the Riemann sum, the limit of the Riemann sum. Okay, and then finally we do the calculation. So if we okay, so the integral of x is x squared over 2. So they divide that by 2, you get 34,300 x squared from 0 to 1/2. When you plug 1/2 in here, you get 1/4. So you get that, which is 8,000 575 joules.